And the rain came down, and piglets started bailing. Okay, we're here for AP Physics C, E&M, and we're continuing our series of video on inductance. Today we're going to be talking about inductance as like a definition and flux linkage, and we're going to be taking a look at a solenoid to do this. So in our prior videos, we've started to see that an EMF can be thought of as Faraday's law, which is an electric field dotted through some closed path integral. So we're looking here for some electric flux, so to speak. No, that's not true. It's just an E field dotted through the integral. But this is a change in magnetic flux in some amount of time. Okay, so d flux dt. And the negative there is Lenz's law because it's opposing motion. Okay, so that's what we've previously known. What we're going to talk about today, though, has to do more with the objects themselves that are creating some amount of what's known as an inductance. And basically, if we take an object, just like a wire, and we're able to make closed loops out of it, there can be some amount of flux that will pass through it to generate a EMF and a current here. So we have this idea of inductance, which we're going to use the letter capital L to describe. This is inductance. And the definition of inductance is the flux linkage, which is kind of weird. That's a weird way of saying things. It's the flux linkage. And technically it would be the magnetic flux linkage for this. Passed by the conductor per unit current. Okay, so per some amount of current there. Now, if we take a look at this definition, what would this mean? Well, this would mean that the inductance is going to be some flux linkage, whatever that is, divided by some amount of current. Now, the way we define a flux linkage is some magnetic flux moving through a area region. So, the B field moving through some areas. We've talked about flux before. And since it's flux linkage, it could be going through n number of loops. This is an inductance. Okay, so that's the idea of that. And we can really get these off of solenoids. So if we have a solenoid, if you recall, a solenoid can be thought of as a number of turns. Boop, like that. And what's going on here is our current is passing through in directions. And as this has a current through it, we could also put a B field running through it as well. Okay, and I guess for reality, the solenoid is actually going to make a B field that way. But this solenoid itself could have a B field going through it. And because of that, it could have some inductance, and as such, we call it an inductor. Okay, our units of inductance are going to be henries, which is just a capital H. In henries, 1 Henry is equal to the idea of a Tesla meters squared per amp. And that makes sense because magnetic flux is Tesla meters squared, or you could call this a Weber per amp. So Webers are W's per amps. Okay, not work, that's a Weber, it's a unit of flux. So it's flux per some amount of current, and we call that a Henry. Okay, so that's our kind of unit of inductance there. Now, if we wanted to take a look at this for a solenoid, how could we do that? Well, for a solenoid, we would have each of these hoops here, 1, 2, 3, 4, 5, 6, whatever, however many loops. Each of those n loops is going to get some amount of magnetic flux, or some magnetic flux passing through it. Okay, that's our flux linkage right there. Now, this flux linkage, in our case, could be equal to, for a solenoid, if you recall, it can have some turn density, little n, that's the number of loops per amount of length, multiplied by some amount of length. And if that doesn't make any sense to you, go back and check our solenoid video for how we talked about a solenoid, because we're going to need it for this and for our next move. Because we need to say, hey, look, what's the B field going through the solenoid, and then the area of those loops. Well, we know the B field that a solenoid is producing here. This B field of the solenoid, we've derived that previously. And what we know is that we could write this once again as NL. The B field of a solenoid is actually given by mu naught I times the turn density N. And we can multiply that by some area. Now, a really cool thing about this is that we also know that magnetic flux is equal to a B field dotted with some area vector. So what we can say about this is our left side is going to become NBA, and this is going to equal here mu naught N squared LAI. If we take a look at this, there's some things that we can kind of clean up here. Well, if we, how do we want to talk about this? We can turn this just back into a flux. We converted it just here using this equation, but we don't have to change that just yet. We might as well just keep it in terms of the magnetic linkage. So if we divided each side by a current here, this would be N flux over I. So this now just became the inductance. And if we also divide this by L, we have the inductance per unit length for a solenoid, which is given to us just by mu naught turn density squared multiplied by the area. So this gives us inductance per unit length for a solenoid, which is a very useful thing, because a solenoid, it could be long, it could be short, but what really matters here is what are the size of the loops on that solenoid and how tightly are they packed together. So is it a big loop or a little loop, and are the lines packed like or are they packed boom, boom, boom? That's what we're looking at for our solenoid case here. Okay, just what are you looking at here? So this is for a solenoid, and it allows us to think about our inductance per unit length here for that. Now, why will this be helpful? Well, in our next video that we're going to see, we're going to take this idea of an inductance per length for a solenoid, and we're going to look at how solenoids can have self-inductance, where as you just pass current through a solenoid, it is going to induce a current in an opposite direction. So we'll cover that in our next video. It'll be a big thing. We talk about RL circuits and LC circuits, which are going to be coming up in future videos as we get there. But for right now, we just need to think about this idea of an induction per unit length for a solenoid given by this. A quick little derivation to get it for us and what induction is in and of itself. Okay? So with that, I bid you adieu, adios, and take it easy.